So I'm going to attempt to talk about the next 50 years. And it's interesting to do so. I happen to live, or we happen to work in a Daniel Burnham building, which is 118 years old. And so it was a modern building of the modern time at the time, but it's still useful. But we would not design the building I'm in today the way it is, because technology's moved on. And so I'm going to talk about the future of tall building technology. And as always, trying to predict the future is always dicey, but here goes. But first, let's go back to what is a tall building and what is the technology that makes it a tall building? And the technology in the skyscraper, I'm going to go back to the home insurance building, which is sometimes considered the first skyscraper, sometimes not. But what were the two things that made it the first skyscraper? The structural system and the vertical transportation. And those are the things that are still quite dominant in tall buildings. The home insurance building had this steel structure that was fairly new technology at the time and had the Otis elevator, which enabled them to safely live far above the ground. And later, other technologies came in. You had air conditioning coming in, should say good or for bad, telecommunications, power systems, new materials such as concrete. And so where are we today? There's been a huge number of buildings. This from the council's database. The tall steel buildings. This is over 150 meters. The concrete buildings. And you can see how dense they are. And then the composite buildings, which is really kind of dominant, where you try to use the right material for the right thing. Concrete and steel together is quite common. And so, and there's been this huge boom. This is the buildings we've done that are over 300 meters tall, just in one office. And it's been just this huge boom of construction. And over this timeline, we've gone from the home insurance building, say a few years later, just approximately 25 years later, 30 years later, to the MetLife building, then jump forward 100 years to the building down the street. So if the home insurance building was the marker at the beginning of the skyscraper era, let me just use the Burj Khalifa as an example of today. You've all seen it. It's basically a concrete structure or it's my friends in the steel industry, I always tell them it's the world's tallest steel building with a large foundation. It's primarily residential, some office, hotel, and it's the structure. It's a concrete structure. The technology, driven a lot by construction considerations. The vertical transportation. Very, very sophisticated. Double-decker cabs. This is the most shafts we have in the building ever. 19 shafts. I think there's like 34 elevators and 19 shafts between sky lobbies and reusing shafts. Very, very tight. There's like no square meter left unused in the building. Very, very efficient. And the technology, from Otis actually did this one also. The technology of elevators with the express elevators, sky lobbies. Freight elevators that go 500, half a kilometer in the air. That's one technology that's been bypassed in the last few years. You can actually even go higher than a half a kilometer with one shaft. Elevators that you use for evacuation of the tower in case of a fire. There's abilities to inspect the shafts to see if they have smoke, and you can use. The fire marshal can use elevators to evacuate the building if they choose. Sustainability, the very sophisticated systems. Luc Leon, who I think is here, did the mechanical engineering on this, and it was about sky source sustainability. We're using better, cleaner air from up high for the building. Pulling your air in as high as you can because it's cooler, it's got less humidity, and it's cleaner. Another thing that was very, very important about the buildings of today is the wind engineering. Between, the previous speakers have talked a lot about that, about how these buildings have to be designed with major considerations of wind, and how wind is now the dominant controlling matter in tall buildings, and you either address it by shaping the building or shaping plus stamping, or both. Then the engineers have the ability to tune these buildings like musical instruments to avoid, the residents, to minimize the behavior so that they're very, very calm. They can be very calm in these windstorms. And so, this is the technology that we have today. The amazing materials we have today, we shouldn't even call it concrete. We should call it something else. It is such a different material compared to what our ancestors had that we use on buildings. The construction technology. My goodness, Samsung is here in the conference, and the ability to pump concrete 600 meters in the air, completely amazing. And then these vertical factories, which we call high-rise construction, that go up and up and up until you have the building that we have today. So, but let's look it forward. Okay, so I showed you where we started. I showed you where we are today. Where may we go? And I think the buildings in the next few years are going to be very different than what we build today. And there's some disruptive technologies coming along. One of the things is the structural systems have evolved, and they should continue to evolve. Here is the chart that we often use in the office about structural systems versus various heights. But what's going to come next? Can we grow? Can we come up with new systems that we haven't done before, that we find that are interesting, that will lead us to new architecture because it's more efficient? That we can come up with architecture that is new and different and interesting, but actually also better. In the office, we've been doing a lot of research in topology, structural topology, to see if we can come up with new architectures and looking for opportunities to apply these to the design of new tall buildings. The wind, I think in the very, very near future, well, not very near future, in a few years away, I was talking to Duncan Phillips just a minute ago. It'll be maybe a few years, but at some point CFD will be maybe partially replacing the wind tunnel. It's not there today. You cannot generally get a building permit with just CFD. You have to do a wind tunnel test. But it's available today for people to use for conceptual design if they wish. But it's still a technology that is evolving. It's not there yet, but hopefully it will in the next few years. This is a big deal. The guys in the corner over there, and the guys who have the rooms around here, all the vertical transportation is going to be a big deal. I think this is going to be one of the biggest changes that we see. Is the elevator innovations. It used to be every elevator went up to. You had to actually have an elevator operator in every elevator. Every elevator went to every floor. And to that, you go forward to, sky lobbies, double-decker elevators such as the Sears Tower had, the Willis Tower, to these, destination control. Soon, perhaps, we'll get to where we have these multiple cabs in one shaft. And perhaps at some point that we'll have these elevators that go not only vertically but sideways. And this is going to have a big, big impact. It's going to change a lot of what we do in the design of tall buildings. Here's a building that I got from one of my colleagues, David Shook, where if you look at the core, the core is used by everyone. It's used by a lot of times the backbone of the structure. It's where the vertical transportation, the egress is, all the mechanical, electrical, plumbing comes up through there, usually. And a lot of the things are going to get smaller. If you take away some shafts, if your vertical shafts are smaller, if you have fewer elevators, you're going to have to come up with new solutions. If we took this building and took it conventionally and we looked a few years forward, all of a sudden that core is going to get a lot smaller. The efficiency is going to get a lot higher from a developer's point of view. This is good. But structurally, it's no longer going to have the impact that it used to be. We're going to have to supplement it with other systems. Maybe we do like your building in New York, where you turn your whole building into a giant I-beam, and put the walls at the edge. Big deal. We really need to embrace this. A couple of weeks ago, the UN had this big announcement about that if we're going to do something about the climate issues, we got to do it soon, and we got to do it for real. And it's going to be, it's on us now in very few years. So what can we do? As we all know, a great deal of the carbon generated in the world comes from buildings. And so, a lot of it is operational carbon, part of it. And so, there's a huge move to renewable resources, but I think our buildings are going to be, a lot more pressures on our buildings to be much more sustainable, both in the operational carbon and also in the embodied carbon. I think it'd be quite interesting if we were all forced to publish the embodied carbon of the construction of our buildings. And over time, this is going to be much more important because, if we're able to fix the operational carbon issue, we still have to address the embodied carbon. It was interesting that this conference had a whole track on timber. There are a lot of people in the industry who are trying to address this thing through sequestering carbon in the construction itself. And I think that that's an interesting thing. And there's a lot of talk in some of the sessions about how tall do we really need to go. I think the Burj Khalifa does an incredible thing by making a sense of place. But if you look at all the buildings around the Burj Khalifa, a lot of them are not that tall. The Burj Khalifa makes the place. It makes the economic driver for everything. But the surrounding buildings could be maybe accessible to other technologies such as timber. And it's not just timber by itself. It's timber with concrete. It's timber with steel. It's maybe timber that's part of the formwork that you leave in place, that's composite with the slabs. Most of the carbon in a tall building, or a good portion of the carbon in a tall building, maybe half or sometimes more, sometimes a little bit less than half, is in the floors. Can we address at least that part of the problem? We talked about glass and energy. It was that glass in the 50s, like inland steel, was this technical opportunity. Then became an economic liability in the 90s, and now it's an environmental liability. And so but can we turn the glass into energy generation? That single move would completely change a lot of our architecture, to where you could have both views and power if you could really generate sufficient energy off of your glazing. Materials, we're going to see stronger, stiffer, lighter materials. This is a steel which is about, 2.5 times stronger than the steel we typically use in buildings. It's very ductile. You can see they took these coupons and bent them around. It's not yet in the structural trades, but it's more in the manufacturing side. But that is coming. And these metallurgists working with the supercomputers are able to design alloys that in the past it would have been too expensive to go through the development process. I got this isn't actually not my slide. I got this from a professor at Northwestern University, Professor Shaw, who's doing work on the stiffness of concrete. Just by adding nanotubes in suspension, 0.1% by weight, can increase the stiffness of concrete remarkably. Because buildings are driven by strength and stiffness and weight. Can we address all of those? And it'll change the nature of our buildings. They will look different because they will be different. Can we, going back to floors, can we come up with lightweight floor systems, such as the research that's going on down in Zurich, over in Zurich, or some of the research going on in Berlin right now of this, they call it infralight weight concrete, which is actually insulating concrete. It actually reasonable strength and insulating properties. So you might go back to the buildings we had in the past, such as the Brunswick building in Chicago, which is exposed concrete, where the structure was the architecture in a very direct sense, and you glazed into the structure, that is no longer acceptable because of the environmental issues, but could come back again if we had this new technology. Construction technology, a lot's going to happen there. We saw in the timber presentations about how they have just incredibly small crews on the site to build these buildings. And when it's all done off-site in factories, everything's done there. But there's a lot of research in 3D printing. Will it come to tall buildings? Not so sure. But it's certainly a lot of research there. Very sophisticated formwork systems, which can be made through maybe, in this case, sand castings, that can lead to, formwork systems which are maybe integrated with all mechanical systems, which is always got to be a little careful on that, but that have, very, very efficient shapes. This is research we're doing with University of Michigan right now on trying to come up with, structural construction, subletting, partitions, all these issues that come into, can we come up with a new, very interesting, very efficient architecture, which is also quite interesting. Can we also do this with not only in concrete? There's a lot of work in 3D printing of steel. I have to. Where's Ron? Okay, okay. So Ron and his crew are doing some very good, interesting research on and just taking some of the elements we have today and doing them better, such as these concrete filled steel plate shear walls, which they've done a great job in developing and promoting to the industry. As can building services get smaller, we're looking for that, and I think it's definitely going to come, and that's going to change. We spend so much time in office buildings trying to figure out, coordinating the services. There are a lot of presentations about coordinating the service and how the M&E between your twin buildings, trying to plug one building into the other, which is an interesting idea, by the way. Can we have these mechanical systems? Can we take the ducts we have and make them smaller? Can we get rid of the ducts? Can we do local servicing? All of a sudden, that 1.2 meters, 1.5 meters ceiling sandwich could go maybe a lot smaller, and you'd have a lot higher efficiency in a different area. And all these things are going to change our architecture in the future. There's going to be a lot of stuff going on in artificial intelligence and machine learning and image recognition. Here's some work that we've been doing on machine learning and construction. Here, this is earthquake in Mexico City. Went down there and took some photographs, and we trained a machine to find structural damage through the imagery. We're working on doing some research. Can we use this machine learning to do rebar inspection to see can it find the rebar and see if it's actually what there's all this photography that's going on sites now. I mean, every job site is just an amazing amount of photography going on. Can that data be used to actually for quality control for our construction as it goes forward? Can we use it? I'm not so sure this is going to work, but we're actually trying to use machine learning to look at shapes from wind tunnel testing. Can we take all the data we get from our wind tunnel testing, put it in, and see if we can learn what are the kind of basic rules that I think we know somewhat just through experience as to how to shape a building to decrease the forces. Can there be a new design process? Definitely. We're currently working with MIT on some of their multi-objective optimization. This is one of Scott's building, where we're actually using these, where it actually learns how, using the grasshopper scripts, it learns how to adjust the shape of the building to maximize the efficiency of the tower. Seismic, big deal. It's a very big deal in China. It's a very big deal in a lot of tall buildings. Can we, let's see if it runs, yep. Can we come up with new, this is some research we're doing on trying to come up with new connections that will be able to dissipate energy and not get damaged by the earthquakes. Right now, our approach to earthquakes is to basically bend the heck out of the structure and then maybe hope to repair it later. Can we have something that'll be stiff under wind, but if it tries to overload, it will relax and breathe. We're looking at ways to have, can we have fuses in buildings that protect the bracing? There's a lot of work that Ron's done on performance-based optimization that can really change the architecture. Can you get rid of that perimeter moment frame and just use the core if you do it right, and end up with this incredible architecture space that wouldn't be possible without performance-based design. Transportation. This is going to be a really big deal. We talked about whether or not this happens or not. Can we have autonomous delivery of materials, such as can all your garbage be picked up off your roof? by a drone rather than by a truck out in the alley. This would actually help on New York a lot, so they wouldn't have to put all the garbage in the streets. They could put it up on the roof and have the drones come and pick it up at night. You know, this is on us now. What's going to happen to our cities, you know, with the autonomous vehicles and stuff like that? The way our cities will function will be quite a bit different. You know, will we spread out, or will we be concentrated in our development? Burj Khalifa has roughly over 1 million square feet of parking. Okay, you would not have to build that in the future. Think about that. Or we're actually designing buildings that have parking levels that are convertible to office space, because after a while we're not going to need those parking levels. You know, so you know, here's a view of the future from the past. Here's my view of the future, which I'm sure will be quite different what I projected, but I do know it'll be different from today. Thank you.